Right, hi everybody, my name's Steve Arnold. I'm the Regional Vice Chair for the North East CIBSE. I would like to welcome tonight Sophie Parry from Zumtobel, who's going to give us a presentation on the Well 2 standard and the lighting which is applicable to that. So I'm just going to hand over now to Sophie and let her get on with it.
Well, thanks very much, Steve. Good evening, everybody. I should add as well, I think the hat I'm wearing tonight to make this presentation, I'm also the chair of the Technical and Publications Committee for the Society of Light and Lighting. So it's my team and myself that put out all of the CIBSE SLL lighting guides and lighting literature that you may be familiar with in varying degrees. I think we're up to about 25 volumes at the moment, but yeah, we'll wear that hat tonight. The fact that I work as a consultant for Zumtobel Group is perhaps just a by the by. Okay, so Well 2, the Well 2 building standard. Most of you probably know by now that the Well 2 standard is a whole building standard. It covers all aspects of wellness. Not just lighting, but we are only going to talk about lighting tonight. And we're up to Well 2 now. We did start off with Well, and then we went into Well 2 formally earlier this year after a pilot study to see how buildings got on with the certification. There's two categories to Well 2. There's owner occupied and there's Well Core, which should perhaps give you a little bit of a clue as to the future of Cat A projects. So Well Core basically means shell and core in English. I should explain at this point as well that the Well 2 standard actually originates in the USA. So some of the asks and requirements are a bit Americanized. We've Europeanized them with the Well 2 Foundation's consent as far as possible for the UK and Europe, but there is some Americanisms in there every now and again. Right, so we're just going to look at lighting tonight out of this collection of various categories. And it's pretty much like BREEAM. We've got this point system. So you decide at the start of the job overall what level of certification you want for your building as a developer or an owner. And you might say, I'm going for Well Gold or Well Platinum. And you can see roughly how many points you need to get to achieve that threshold for that certification once the project's complete and has been verified. And this is for all of the categories, but you can see that lighting does make a significant contribution to the points at the various Well, Silver and Gold, Platinum levels. So it's quite a big subject within Well, and quite rightly so. So yeah, and then once you've established what point you're going for, you have to then look at all of the areas of Well and decide where you're bringing your point from. And you can't just load it with one or two of the categories. It has to be an even spread. And some of the, in each category, some of the items are mandatory and what we call a prerequisite, and then others are optional by American standards, but usually we do in Europe and the UK as standard anyway, because dare I say it, our lighting standards are a little bit higher for day to day. So that's how it works. So we're going to talk tonight about lighting, and a big part of lighting in Well 2 is melanopic weighting, or the non-visual aspects found in daylight, and how these can be transmitted into the building if you're doing daylighting engineering. But in Northern Europe, quite often we can use daylight some of the time, but more often than not, we have to supplement it with electric lighting, certainly at this time of year when the nights draw in and we don't get much daylight in the daytime of any applicable strength. So you'll hear me talking about melanopic lux, melanopic lighting. So what am I talking about? So let's try and break this word down and explain what it means for those that don't know. So basically, in daylight, if we use daylight as a standard, there are two main components. There's what we call the visual or photopic component that allows you to see things, and there's the melanopic component, which is nothing to do with vision, but it's present in daylight. And what the melanopic component does, it's picked up by separate sensors in the eyes, and this information is transmitted to the brain, and it basically controls the pituitary gland, which the pineal gland, which releases or suppresses the melatonin hormone, which either makes you feel relaxed or alert. And by doing that, it also recalibrates your body clock each day. So this kind of explains that when you go outside and maybe spend a day outside on the beach or in the garden or doing what you like to do outside, at the end of the day, you probably feel a lot better in yourself. And part of the reason that you feel a lot better in yourself is you've probably had a good exposure to daylight, whether there's cloud cover or not. You'll still get a melanopic response from cloud cover, which is what we call diffuse daylight. And this phenomenon, if you like, or this circadian alignment is most prominent usually in the mornings, around about mid-morning to early afternoon. So this is when we get the best dose of melanopic lux from daylight, whether it's diffuse or direct. And also during the day, the color changes, the sun changes color temperature as received on planet Earth. So the sun, if you're familiar with electric lighting, you know about 4,000 Kelvin, 3,000 Kelvin, that sort of thing, warm white, cold white. Well, the sun does exactly the same thing. As it moves across the sky each day, the color of the sun appears to change color temperature. And it's not actually the sun changing color temperature, it's the color of the light entering the Earth's atmosphere, and the color shift occurs between the upper atmosphere and actually arriving at the surface of the Earth. So the sun is a constant in terms of temperature. It's just the atmosphere at different angles that changes the color temperature. So first thing in the morning and last thing in the afternoon, you'll get this lovely rosy orange glow as the sun is just on the horizon, which is around about 2,000, 2,200 Kelvin. This basically allows your melatonin hormone to start to build up. So it gives you that relaxed feeling, especially in the afternoon when you're knocking off work maybe and going home. And then you probably destroy the effect if you've got harsh lighting in your home and you switch that on. But that's the general idea. It's a primeval response. So when you get sun at dawn or sun at sunset, and it's that nice reddish orangey color, basically that does not suppress your melatonin hormone and it makes you feel a little bit relaxed. But during the day, as the sun gets higher in the sky and turns to a whiter color, then the melanopic content of that sunlight will suppress your melatonin hormone. So once you get up in the morning and you get out and about and you feel that you're most alert, part of that's because you've obviously hopefully had a good night's sleep, but also because your melatonin hormone is being suppressed and therefore your body is at its most alert, and at the same time you're realigning your body clock. So that's the science behind it. And what the reason I'm telling you this is what we are doing with electric lighting these days, especially since the advent of LED, is we are replicating as far as possible the non-visual effects of sunlight indoors with electric lighting, where we've introduced a melanopic response that has to also be delivered by the electric lighting rather than just a photopic element that allows you purely to see things, which is what we've been doing for the last 120 or so years since we invented the electric light bulb. It's just purely delivered photopic light to allow you to see things in the absence of daylight within a building. And that's meant that people have started to come indoors more and more, perhaps to do their work, to study, and so on and so forth. So we perhaps don't get as much sunlight as our ancestors used to get. And yeah, there are some disadvantages to that because the electric lighting indoors for many years has not delivered that melanopic content. But we're now where we are with lighting technology, where we can deliver melanopic content as far as the science allows. And we are doing this, and this is what lighting in the World 2 standard is about in part. And this is quite a new subject to most people involved with lighting. So tonight, although we're talking about the lighting element of the World 2 standard, when we look at how to design, we are going to major on the how do you calculate and achieve the melanopic content that you require for World 2 certification. So let's just look at it perhaps from a technical or an engineer's point of view. So that trace you see on the screen here, this is daylight. This is a daylight spectrum in Northern Europe. So this is, if you like, where ultraviolet finishes and infrared starts. So between ultraviolet and infrared, you've got the visible light spectrum, which is represented by this chart. And what you'll notice on this chart is the wavelength is on the horizontal in nanometers, and the amplitude or the spectral power of the visible daylight is represented on the vertical side of the chart. So there's two main areas there. There's the green hump, the V lambda. That's the photopic element I was talking about. That's what allows you to see things. So when that's delivered in daylight, it bounces off a surface into your eyes, and then your brain interprets what you're looking at in terms of colour and texture and hue and things like that. The other noticeable hump, this blue one, C lambda, this is the melanopic content. And you can see it's quite significant as well. This does not aid your vision whatsoever, but there are other sensors in your eyes that can pick up on the melanopic content. And what it does, it sends separate signals to the brain, and this regulates your hormones and recalibrates your body clock, provided you get exposed to it. And that's been the problem over the years. If you're outdoors, you will get exposed to it, and you only need a few hours each day. If you're indoor with poor quality electric light, and perhaps in a deep pan office where the daylight doesn't really penetrate, you're not going to get your dose of C lambda, and that's what we're trying to put back in with electric lighting via the WELL 2 standard. If we then look at electric lighting, if I can just get this to nudge on, we have something, so this is the same trace of visible light but delivered by an electric luminaire, an LED luminaire, which has got what we call enhanced spectrum. So you can see that the energy levels across the visible light spectrum are quite high there, particularly in the blue going on azure. This little bit here, there's a nice peak there, which is the melanopic peak, and then you've got a certain amount of energy here, which allows the photopic version to work and also give you good quality color rendering. So this is quite a high-end LED luminaire, if you like. These others here, the top one here, this is a CRI 80 luminaire, typically used, say, in offices and education. You'll see it's got a bit of a blue peak in it. It doesn't quite come over into the azure, so it doesn't have a very high melanopic content. All it does basically is deliver a useful photopic content to allow us to see things. If we wanted this photopic content here to be at the right magnitude to trigger a circadian reaction, within the people in the space, we'd probably have to illuminate the space to around about 900 to 1,000 lux, which is not a good idea because it will be overlit for most people and it will be using too much energy. So that isn't really a viable engineering solution. If we come below to this bottom trace, this is a CRI 90 luminaire, so a little bit better than a CRI 80 luminaire. And you can see we've got a bit of a blue spike, but we've got some more energy as it goes into the azure. So this starts to support a melanopic response, and then we've got good richness throughout the photopic content. And the charts below basically break down each colour on the CRI scale to their relative weighting, and there's a big difference, if you like, especially on the red between a CRI 80 and a CRI 90 luminaire, and then when you go up to what we call a spectrum enhanced luminaire, which is the very latest LED technology. But it's really CRI 90, what we call tunable white luminaires, and these enhanced spectrum luminaires that we need really to engineer an elegant solution to deliver a compliance with the WELL 2 standard on lighting. So let's start to break it down then. Let's actually look at section L of lighting in the WELL 2 standard. So as I said at the start, you can't pick and choose which sections of the WELL standard you're going to collect your points from. Each one has preconditions, each section has preconditions. So for lighting, there are two preconditions. The first one, LO1, you have to look at daylight availability. So you really need to do a daylight study on every project to see how much available daylight is penetrating the space. And from that, you'll know how much melanopic light as a free gift from nature you're also putting into your project at certain positions where people might do a job of work, for instance. Then the other precondition is LO2, which is visual lighting design. So this is the design of the electric lighting. So in most projects that are indoors, whether it be education or office or industry or something like that, but let's use office as an example. We have BS-EN 12464 Part 1, which is the default lighting standard that most projects are specified to and work to. So rather than using an IES standard from North America, which should still be an imperial measurement rather than metric, so we'd be talking about foot candles, Well2 have agreed that we can use the regional standard for Europe, which is 12464 Part 1, which is obviously metric and uses SI units as well. It was actually revised and relaunched on September the 1st this year, so it's a little bit harder to achieve in some cases than it was against the 2011 version. So that's a subject of a separate presentation. But yes, you have to know your way around 12464 Part 1, particularly with the 2021 version. Otherwise, you will end up with a project that could be overlit and perhaps using a lot more energy than the sustainability manager would like. But then once we've achieved LO1 and LO2, which we have no choice, they're preconditions, we then look at optimizations, and there are up to 8 optimizations, and as you can see, they all attract points. So this is, where the points are perhaps going to come from to deliver the level of well certification and contribute to the overall building. So if we look at LO3, which is perhaps the one that causes people the most work, really this determines how much melanopic light content we need to deliver from the electric lighting, and it's all dependent on the output of the daylighting report. So really, before you can start to design your electric lighting to comply with Well2 and LO3, you'll probably have this on every project, because what it says in LO1, which is a precondition, remember, is if you can't deliver all the melanopic lighting required from daylight alone, which is very difficult unless you're going to put everybody in a greenhouse or an atrium, then you need to deliver it via the electric lighting. So quite often you will get some melanopic light from daylight, so it's going to be a blend of the two, but depending on the output of the daylight report, you've got 2 options here. So if you're working with electric light only, if you design for 150 equivalent melanopic lux, which if we convert that into the latest SI unit, which was incorporated into Well2 earlier this year, that's 136 melanopic equivalent daylight illuminance at daylight 65, which is 6,500 Kelvin, and that will give you 1 point if you deliver effectively 136 MEDI. If the client wants to go a little bit higher and they ask for 250 MEDI, which is 275 equivalent melanopic lux, then you can attract 3 points. And a lot of projects tend to ask for this, especially in the early part of the project development, in the absence of any other information, because this is the highest number really. And also this is about the trigger point that the lighting industry, the global lighting industry, or the scientists behind the global lighting industry at the CIE recommend is the level to head for before you actually get a response in human beings and actually trigger that melanopic response, because it obviously has an excitance or a trigger point. So that will give you 3 points. You've got option 2 where you've got electric light and daylight, so you've got a blend here. So you have got some useful daylight coming into the building with a melanopic content, but it's probably not penetrating everywhere or to as many workstations as a percentage as it should do, and so therefore you have to supplement with electric light. So what you can do here, you have a choice. You can either go for 120 equivalent melanopic lux, which will give you 1 point, or 180 equivalent melanopic lux. So not quite so hard to achieve, because you have got some melanopic lux within the daylight coming through as well. So if you were going for 275, it's probably because there's lack of project information available and people are being cautious, which is fair enough, and maybe you'd relax or reduce that number as you evolve the design, maybe up to stage 4 and more daylighting information became available to the design team. Or, if you did have a good daylighting report and the daylight engineer said, look, I am delivering some melanopic lux with the daylight, but not everywhere, then you can decide from option 2 which one you want to go for. But you really need to know, because to deliver 275 is perhaps the most challenging lighting engineering part of well 2. So if you can get the daylighting information earlier and you can get a lower number, it just makes your life a little bit easier. But I know we don't live in a perfect world, so that's not always going to happen early on until you present the costs, and then probably magically that information will appear, and you can correct it on the next design iteration. So the next one is LO4 glare control. So there's two parts to this. So what we're talking about here is glare from two sources, possibly glare that comes from the daylight coming through the windows, delivering the melanopic lux. Also, perhaps at certain times of the day or year, also introduces discomfort glare. So we're going to need some form of shading control. It could be as simple as manual pull down blinds. Or it could be an external arrangement, and both options could be motorized and automated and linked to the lighting control system. But yeah, you do need to think about shading for two reasons. First of all, discomfort glare is not funny, and also if you've got too much daylight coming in, especially in the summer months, you might have a solar gain problem, so therefore your costs to cool the building start to go up as well. So it's a bit of a double-edged sword on how much daylight you are going to let in, and how you're going to control that daylight so that you don't have a problem with solar gain and also discomfort glare, which makes it quite interesting when you're engineering it. Part 2 is probably about the glare characteristics of the luminaires. So you probably know that when we're working in, say, an office or an educational environment, for instance, where people spend any length of time, then we need to use luminaires with a low, what we call UGR value, or unified glare ratio. So we can't use just any old luminaire, because the longer you sit in a space, if there's a problem with glare from the luminaires, especially discomfort glare, the more irritating it is on the eyes and the less productive you become as the day goes on. Or if it's a classroom or a lecture theatre, the less information you're able to take in, because your eyes are starting to feel a strain. So they will talk about various options you can employ to get the 2 points. So option 1 is using indirect lighting, so where all of the light from the luminaire shines straight up and is bounced off the ceiling. So you have this indirect lighting effect. Bearing in mind, you've also got to deliver melanopic lighting as well via that indirect lighting. So this is where it gets multi-dimensional, where you're designing what you give with one thing, you might be taking away with another feature. So you have to have your wits about you and do a few of these projects to get the feel for it. Your other option, which is more popular in the UK, is to use low UGR luminaires. So if the luminaires are going to be mounted at 5 meters or below, it's asking for UGR 17. Now, this is a bit of an odd number, and the Americans are not too keen on moving it at the moment. It should either be 19 or 16. That's the way the UGR scale works. And I have spoken to the Well 2 organisation about this, but I'm not getting a very satisfactory answer as to why they insist on 17. If you've got higher luminaires above 5 meters, then you can have UGR 20. But most projects usually go for UGR 19 in the UK and Europe, and we can get that information off the data sheet, but that's only relative. So when you look at a luminaire data sheet and it says this luminaire is UGR 19, it was UGR 19 at the ceiling height and spacing that it was measured in the laboratory to create that data sheet. So if your project has a different ceiling height, for instance, as to the laboratory that cut the data sheet, and it almost certainly will have, then your UGR will be different. So you can't really just take the statement off the data sheet. That's just a relative indication that you're in the right ballpark, that it's been designed to be a low glare luminaire, but you really should model it as well based on the spacing and the ceiling height on your project. So you may have cut a Relux or a Dialux model, for instance, and there is a feature in Dialux where you can actually check the true or the more accurate UGR relative to your project, and that will give you an indication that you're perhaps where you need to be. But you need to try and engineer it down ideally to 17. This is the first contradiction in Well 2. In LO2, it tells you that you can work to BSEN 12464 Part 1, which would only require a UGR of 19 for an office project, and that's a prerequisite in Well. But the optimization then pushes you towards 17, when actually it should be 16 or 19. So sometimes we get projects where the customer's adamant they want 16, which means that we have to put the luminaires closer together and it uses more power than they would like. So it has to be a bit of a trade-off, and you have to perhaps understand how to articulate this to a customer to say, well, you know, that's what you're asking for because you've read it somewhere, but this is a consequence of what you're asking for, and actually there's a different way to do it which is also acceptable, and maybe go for 19, or maybe you just don't go for those points. And then option 3, restrictions on shielding angles depending on the luminous intensity of the luminaire. Well, we do this anyway when we build a luminaire. There's 2 parts to reducing glare in a luminaire. There's the mechanical shielding angle of the reflector, which is usually limited to no more than 65 degrees. And for many years in the US, they just purely worked on that mechanical angle. If it was 65 degrees or less, it was a low glare luminaire, put it in the job and forget it, job done. And then recently, with the advent of Well 2, they discovered UGR as an addition to the mechanical side of the luminaire, and that you could actually have values and do calculations. Now, we'd been using them in Europe for many, many years. They've been around for many, many years, but they didn't bother with them in the US until recently. So my colleagues in the US are spending a lot of time doing presentations to consultants explaining what UGR is and where it fits into lighting design and what the benefits are. So again, you know, option 3 is a bit of a funny one because we would do that as automatically in the UK, and we would also look at UGR anyway. So option 2, option 3, it's everyday business to us. It's nothing special. Moving on to LO5, enhanced daylight access. So this is an architectural thing. So this is really looking at that daylighting report and, you know, are they really opening up the envelope of the building to let as much daylight in as possible? And is that the design, and therefore how much melanopic lux is it delivering? And this will also influence which section of LO3 you invoke as well, in terms of how hard the electric lighting has to work to deliver some melanopic lux. So again, you really need that information, but again, if proper daylight engineering and reports are done, this can attract up to 3 points. The next one, visual balance. The first element, there's only 1 point, but there's 4 separate elements. There's brightness control, which you can do with the lighting control. We tend to do that anyway as standard in Europe. Visual acuity. This is now something that's part of 12464 Part 1 2021. So if anybody's already had a look at that new lighting standard for interior lighting, you have to go through table 1 and table 2 before you look at the application table relative to your project, and you have to do effectively a mini risk assessment to make sure that everybody using the space is well catered for and they can actually see what they're doing, because not everybody's eyesight is the same level, especially if you've got an open plan office with maybe 50 people working in there. You know, you can't just light for the 21-year-old that sits in the corner when perhaps you've got older but more experienced people sat elsewhere who can't really see what they're doing, and they need a bit more light. So the new standard for Europe takes this into account, and this is what visual acuity is all about. Tasks, again, we're only really delivering melanopic lux to where people study or do a job of work for any length of time. We're not doing it in the corridors, we're not doing it in the WCs. Those are just transitory areas where people wouldn't really benefit from it. So if somebody sat at a desk, whether they're studying or doing a job of work, then that's their workspace where they do their task, and that's where we need to deliver the good lighting and the melanopic content to realign their circadian rhythms, either by daylight or electric light or both, depending on the daylighting report. And then you've got space features as well, so that this could be thing like localized control, for instance, if you've got an open plan office, so that there's not just a few switches in the corner and the boss decides where the light's going to be today to suit their own personal preference, and everybody else has to put up with it. LO7, electric light quality. This is an interesting one. CRI, this is the color rendering index on a scale of 1 to 100. So we talked about daylight earlier. Daylight is CRI 100, and that means it gives you the best color reproduction. So daylight is the best at reproducing colors, and quite rightly so, it's right at the top of the scale as CRI 100. And we work backwards from that with electric lighting. So good electric lighting tends to start in terms of color rendering reproduction at around about CRI 80, but that's now moving towards CRI 90 as LED technology improves. So yes, you can still use CRI 80, but as I said before, it doesn't have much of a melanopic content, so it's not much good where we've got to deliver melanopic content on Well 2 certified projects. So we tend to use at least CRI 90, and basically the Well 2 standard is actually now saying that you know, if you're going, when you're lighting your task areas which are defined, so it tends to be a Cat B project, then, or if it's a Cat A, you have to work to a lighting grid of 9.3 by 9.3 meters. So we would tend to use CRI 90 as standard in the work areas, but other areas such as circulation and WCs and so on and so forth, you can still use CRI 80 luminaires because these are just transitory areas. Flicker is the other part of LO7, and this one again has been quite challenging historically in Europe. So LED lights do flicker. Don't believe what people tell you that there's such a thing as a flicker-free LED luminaire. They all flicker, but to varying degrees. And what was launched earlier this year were two documents which have now defined acceptable limits of flicker and stroboscopic side effects for LED lighting. We couldn't use the metrics from the days of HF fluorescent because a HF fluorescent ballast was 230 in and 230 out, whereas a LED driver is essentially a very stable DC power supply with a modulated signal superimposed over the DC output. So it's a very different way of driving your lighting source, and the old metrics went, if you like, the old engineering methods were not directly transferable into LED, and it's taken a few years to get international agreement. So if you look at some of the early Well 2 specifications, they will say that the flicker characteristics of the lighting has to comply with, say, IEEE 1789, which is an American standard from 2015, where the Americans produced a very early standard on LED lighting flicker. And it covers both mains, rotary type dimmers, and also perhaps dimming introduced by Dali. It's quite a difficult standard to work with in Europe, or certainly outside of North America, because it's frequency dependent. So it's all written around a 60 hertz main supply, which is the standard for the US and North America, probably most of Central America as well. But as you know, on this side of the Atlantic and most of the rest of the world, we use 50 hertz. So where they've put limits and tables, they're all based on 60 hertz, and you have to convert everything down to 50 hertz. So that was always a little bit of a pain. We could do it, it just took a bit of work, but things have moved on this year. So in the new the very latest Well 2 standard, you will find to comply with flicker, you can either still use IEEE 1789, which I'd recommend you don't unless you enjoy maths, or you can comply with NEMA 77, which is another North American standard, but it's actually based on international standards, what we call the IE standards, the International Electrotechnical Commission standards, which we also use in Europe, and it's not frequency dependent. So those same IEC standards that appear in NEMA 77 in the US have also appeared this year in Eco Design 2021 from the 1st of September, which is legislation on luminaires and the limitations that they should now have from the 1st of September by law in terms of the flicker content and the potential for stroboscopic effects in and around moving or reciprocating machinery. So if you look at a good quality luminaire or its driver data sheet, you should see two new metrics, PST-LM and SVM. And provided the PST-LM is equal to or less than 1 and the SVM is equal to or less than 0.6, then these will be okay. So you need a pretty good quality luminaire. That they are readily available in the UK. They're not a rarity, but I would suggest that perhaps the bargain basement luminaires that might end up as value engineering on a project probably won't comply with these metrics. It's probably a warehouse where there's thousands of these things that have been there for a while waiting to be sold. But yeah, flicker used to cause a problem. problem for us, where we're trying to convert American standards, but now we can cite NEMA 77 on the basis it's based on the same IEC standards as eco design and the new BSEN 12464 Part 1 2021, which are staples for the UK and Europe. So you kind of have to explain it and just show how it links across, but that can be done quite easily now. Finally, LO8, ambient lighting and occupant lighting control. Yeah, ambient lighting, it's a bit of an interesting one. It hasn't really been fully developed yet, but it's generally accepted to mean at the moment where you don't try and light everything from the ceiling. That you will have some lighting on the ceiling to light your circulation spaces and benefit the maintenance and the cleaning staff maybe, but you actually have freestanding or desktop lights that are closer to the workstation, so you're not forcing the light down from the ceiling, you're bringing the light source closer to where it's needed, and therefore you're probably using a light source that's using slightly less power than the one on the ceiling to do the same job. And it means you can be more targeted as well, because you could perhaps put you could then break them up into lighting zones, because people tend to sit either at individual workstations if they're lucky, or they sit in a cluster of workstations. So what you can do is you can maybe have a couple of three standers on a 4 or a 6 person cluster of workstations, or maybe you've just got 1 or 2 people with visual acuity problems and you just put a freestander or a table lamp at their workstations, and everybody else is lit to a normal level that they can work to. And also, you know, by introducing this more localized lighting, you can include localized controls such as on, off and dimming switches at these individual luminaires, so people can adjust for individual preferences, particularly if they're doing screen work. So if you're going to do this also attracts points, but I think you'll find ambient lighting is going to have to become more and more popular as we go into the future, particularly as we start to make contributions through lighting to net zero carbon outcomes. Now, the WELL standard doesn't really talk about energy, it's just about the quality of the building and the services in it and the experience it delivers to the end user from a point of view of wellness, unlike BREEAM, which is a blend of energy and wellness. Okay, so that's perhaps the most notable difference between the two standards. So having had that tour, how do we actually put this into practice when we're designing lighting? So if we look at this open plan office area here, it could be an office, could be a study area. You'll see we've got good floor to ceiling fenestration. There are some blinds on it to assist with glare control. They're manually adjustable for certain times of the day and the year. But I would imagine that most people walk into that space, if they're hot desking, they will probably want to sit as close to the window as possible. It's kind of a primeval reaction that is built into all of us. You know, we do like the connection with the outdoors for various reasons. But if we turn this space into plan view and again look at it from an engineering perspective, yes, we've got some daylight coming in, and it will only come so far into the floor plate on this project, and then we'll go deeper into the floor plate, and really there'll be some daylight, but not useful daylight, and certainly not a good melanopic content. So we would have to infill with electric lighting if we were just relying on the daylighting for the melanopic content closer to the windows. So that's the theory behind it, but in practice we would probably say let's design for the 21st of December, where we probably won't have any useful natural light coming in and we'll be totally reliant on electric lighting. And as the seasons go by, if we get a benefit from electric lighting at certain times of the year, great, we'll control that with daylight linking, where we'll basically dim the electric lighting down and let the daylight take over as far as it possibly can by using balanced photocells in real time. So that's the reality for us in Northern Europe. So again, what would we do with this? So what we need to do in this electric lighting zone is we need to deliver the agreed melanopic lux content, as well as the general purpose photopic electrical lighting, for at least 4 hours a day. So the melanopic content has to be delivered for at least 4 hours a day via the electric lighting, unless some of it's coming in with daylighting. But let's assume it's not. Let's say we're going to deliver everything with electric lighting. So we need a lighting control system. So we need to design this lighting to be able to light the space to the correct illumination values and also deliver the melanopic content between 0900 in the morning and 1300 in the afternoon. So for 4 hours each day. So we need to switch, and then outside of that 4 hour time zone, the lighting can just operate as you would expect it to operate. It'll just be delivering the maybe 300, probably 500 lux on the workstations in the way that we always design. So what we're actually designing for is a lighting installation that can do something different for 4 hours of the day in terms of delivering the required melanopic lux, and then after 4 hours just go back to being a lighting installation as we love and know it. So we have to switch between two modes with a lighting control system, so we can automate that, what we call in Zumtobel zone 1 and zone 2. So zone 1 is active between 0900 and 1300, and after that we go into zone 2 where it just switches back to a standard lighting control system. So what you might see to deliver that melanopic lux, depending on your choice of luminaires, is that during that 4 hour period, the lighting level raises a little bit, so the lights appear brighter. Or if you're using tunable white, you may shift the color temperature from 4000 Kelvin to 5000 Kelvin for 5 hours, because also shifting the color temperature will raise the melanopic content to a certain extent. But you don't want to go too far with that, because if you start pushing up towards 6000 Kelvin, people will find the light is too harsh and blue, and therefore you'll have discomfort problems, and the people using the space will start to complain. So again, it's knowing what you can do and how far you can go to make it comfortable for people and who actually want to be in the space. So mode 1, 9 AM to 1 PM, the EML or the MEDI target as LO3, and your color correlated color temperature, or the temperature of your lighting, will be subject to client preference and the energy target as well. So, if the client says, no, I only want 4000 K, I don't care what you do, I'm not having 5000 K, it's going to be 4000 K, then you might have to say, well, we're going to have to raise the illumination levels for those 4 hours to meet the requirements of LO3, which means we'll be burning a bit more energy for those 4 hours. Are you okay with that increased energy consumption? Or if we raised from 4000 to 5000 Kelvin, the energy consumption would stay more or less the same, just the lighting color temperature would shift up a little bit and then go back down to 4000 K at 1 o'clock. So these are the kind of conversations you have to have. And then, of course, when 1 o'clock comes and the lighting control switches everything to mode 2, it just purely becomes a photopic lighting installation again, as per LO2. So it just delivers the prerequisites to BSEN 12464 Part 1. So just to sort of summarize what you'll be working with here, LO1, electric lighting designer will require daylighting report to determine design requirement for LO3, so that you know what your electric lighting's got to deliver in terms of equivalent melanopic lux, or basically melanopic equivalent daylight illuminance. LO2, you'll be working to BSEN 12464 Part 1. The 2021 version has just been released, so if you're looking at a project that's been live maybe for a year or two, it may have started on the 2011 version, and you just need to clarify that you are staying with the 2011 version and not moving up to the 2021 version with your client. LO3 requires the manufacturer's melanopic data for luminaires, so you've got to be very careful with luminaire selection as well. Make sure that they can actually, aesthetically is what the client wants, but also they're capable of delivering the melanopic requirements for those 4 hours, and that you can get hold of the data so that you can actually model and design this beyond reasonable doubt. Otherwise, you're going to have a bit of a problem. LO4, you need to be selecting luminaires and do that are basically low glare, and do a UGR calculation to supplement your design. LO5, the electric lighting designer will require the daylighting report to determine the requirement for LO3. So LO3 and LO5 are all about daylighting and supplements. They work hand in hand. You can't really do it unless you design to worst case, which is 250 MEDI, which is, from a lighting engineering point of view, is actually quite a stretch, really. There's not many luminaires that can do it, and depending on what you use, you might be using a bit more power than you ever imagined as well to make it work. LO6 you just design as LO2. It'll come out, if you are designing to 12464 part 1, it will come out of that anyway as standard. And LO7, again, you've got to have appropriate luminaire selection here, including performance criteria for the temporal lighting artifacts, so that you can do a desktop assessment on the flicker content of the luminaires to make sure they're equal to or ideally below the new metric, which for flicker is 1 or less on the scale. If not, you're probably going to have a flicker. And to be honest, that applies to any project, not just a Well 2 project, but it's only the Well 2 spec if LO7 is invoked in the specification where you really have to check it. And then LO8, clarify if ambient lighting or localized controls are required as part of the design brief. Not everybody likes that. A lot of people like to try and do everything from the ceiling, because that's what we've always done, and that's what they're used to. But I think you'll find, as I said before, as we push towards net zero contributions, then we're going to have to start looking at ambient lighting and perhaps desktop or floor standing lighting next to workstations, and bring the light source closer to where we actually need it. So how do we do this then? So we do our lighting design. There's a typical Cat B office space modelled up in Dilux, so we know where all the workstations are and where people are going to sit. So we just, Dilux can only work to do photopic lighting calculations. It can't do melanopic lighting calculations, but we need to model in the usual way that we would always do a lighting design, using say Dilux or Relux, and we're working in photopic, and we can take that photopic data as it starts to emerge from the design plots, and we can convert it into melanopic to check the melanopic content and back again. So we start off, so this should all be familiar. We've plotted it, we've looked at the average lighting level over the space, but we're not interested in that really. We're interested in what happens at the workstation. So on this page here, this little pink rectangle just looks at one workstation and the lighting levels in that, within that pink box for that one workstation, which is what we're really interested in. And then if we look at it like this, so we understand where we're going with this, is we are looking to deliver vertical illumination. So the melanopic lux is delivered at the eyeball, not at the work plane. So we are delivering our photopic illumination to the work surface. So here is the sort of like orange. So we'd be looking for our, say, 500 lux here. But we also need to deliver the melanopic content in this vertical band here, which is typically 1,200 millimeter to 1,600 millimeter above finished floor level. And this basically captures, for the average height person, somebody who's either sat or stood up. So what we do is we take that green band area and we want to look at what we call the vertical illumination in that area. So we can take a slice in Dilux. We've got the idea there. So this is the area we're looking at. So all of these numbers in this vertical Dilux slice give us a rough idea of what's going on. But remember, we're still working in photopic values, not melanopic. We then need to do a conversion. So to get the melanopic data, you need to look at the manufacturer's data sheet, assuming they've got one for the luminaire. And this is where you've got to be very careful with your luminaire selection at the start. So if we look at this data sheet here, this additional data sheet for this particular luminaire, it provides melanopic data. So this is a tunable white luminaire. So what we've got is 3 columns here: the white, the yellow, and the purple one. These are different, what we call multipliers for different ways of calculating melanopic lux. The one we're really only interested in for Well 2 is what we call the MEER column. And what it shows is it shows different multipliers at different color temperatures. So depending on what color temperature you're going to use to deliver your melanopic lux, you'll see as the color temperature goes up from 2,700 Kelvin to 6,500 Kelvin, that multiplier goes up in value as well. And interestingly, if you look at the lumen output, it stays pretty constant for this luminaire. So we need this level of information from the supplier of the luminaire, and then we need to take this value. So if we're working at, say, around about 4,000 Kelvin, for instance, and we wanted to keep it at that, we'd have a multiplication factor of about 0.8. So if we times the photopic lighting in that vertical slice and times it by 0.8, that will normally tell us the melanopic content, which is obviously going to be a bit lower than the photopic content. And we know what the melanopic content needs to be from the conversation with the daylighting engineer and the requirements of the daylighting report. So that sounds quite simplistic. So if I could just get my screen to move, what we do in Zumtobel and Thorn, we have developed something perhaps a little bit more finite. So remember I said earlier on, if you're working on a Cat A project, you need to use a 9.3 meter by 9.3 meter grid, because we don't know where people are going to sit in the furniture as yet. So that's what's been agreed and it's not actually in the engineering manual for the WELL 2 standard, but it is in their verification manual, which is used to verify or commission the project on completion. So again, with WELL 2, you have to read all of the documentation. Sometimes you find little anomalies and inconsistencies, but what we've done, we've set up that 9.3 meter grid. And so this is a Dialux plot, or a section of a Dialux plot for a Cat A office. And what we've done, between 1.3 and 1.6 meters, we've got 3 points of measurement within that 9.3 square meter grid, and we take that measurement in 4 different directions. So we actually take 12 different measurements here in the vertical in each 9.3 meter grid to get a reasonably even balance, and then it would have to be checked again when the place was populated with furniture. But this generally will put you to where you need to be with a nice symmetrical array of luminaires that will satisfy the architect. And what we do is we do this in Dialux, and then we take the output, we export the data from Dialux, and we punch it into a spreadsheet, and it produces a lot of information for us, which we can then export onto a CAD drawing, and we can put a summary of compliance down the side of the drawing for WELL 2 projects. And then we can start to look at which luminaires might achieve the performance objects. So you can see here we've tested various luminaires. We've tested a 940, we've tested a tunable white, and we've tested an enhanced spectrum luminaire. So for all of these, we need to know what the multiplier is for the melanopic ratio. And what we've done is we've used it. And so if we look at the end column here, we've listed the MER value. So we're working in equivalent melanopic lux here. So that's a number that's slightly higher than the MEDI number. And then that gives us the maximum melanopic content. And you can see here, if we start off with a more simplistic luminaire like CRI 90 4000K, we are getting about 120 lux at melanopic, as opposed, and then if we come down to something with a higher specification, we've got that 240 lux for the worst case scenario. But we can only do that by coming up to 5,000 Kelvin. Yeah, so we started off at 4,000K, which is everybody's favorite, but to actually deliver these higher melanopic contents, we've had to step up for 4 hours to 5,000 Kelvin. So it can be done, and you have to test various luminaires to find out what works best. And you've got to keep one, although it's not in WELL 2, you've got to keep an eye on the power density as well. Otherwise, you are going to have some awkward conversations with your sustainability manager. So most people are looking to limit it below 5 watts per square meter or less, which is, you know, it's a starting point, but it's not the most accurate way of calculating lighting power. You should use the Lenny method, but you know, if you want to work in power densities initially and aim for about 5 watts per square meter, you can then run it by Lenny later on, and you'll get an even better result. So just use that as a starting point. But you can see with these luminaires, we've checked the average illuminance in photopic. We've looked at the UGR that this installation is going to achieve. We've also looked at the flicker content. We've checked the characteristics of the driver to make sure it meets the requirements. We've looked at the watts per square meter that the initial design is going to deliver in both modes. Remembering, if you go into your mode 1 where you're delivering melanopic lux, you might be using a bit more power than you thought. So yeah. So we've looked at it on both sides there. and then we've converted it to Lenny, and we've looked at the lighting energy numeric indicator value, which takes into account the effect of standing loads, which you get with most luminaires, and particularly where you've got emergency light chargers, exit sign chargers, things like that, and also the benefits of having automatic lighting controls such as daylight linking and presence detection. So that's all taken account in Lenny, which doing a watts per square metre calculation won't take into account. So the BCO, the British Consortium of Offices, their Lenny requirement for offices is that nothing should exceed 18 kilowatt hours per square metre per annum. So all of these we know meets the BCO spec, which is the hardest one to achieve in the UK at the moment. The new Part L of the building regulations, when it's published, may change that, but it's not quite published yet, so we'll have to wait and see. So yeah, there's quite a lot of work to do here, but this is kind of the process that we follow to establish the melanopic content and therefore the compliance for well 2. So talked a little bit about verification, and this is where it gets interesting, and I think it again gives me a bit of an idea of where the future of lighting is going to go. So if you go for well certification, doing the design is one thing, but when the project's installed and up and running, then the well assessor has to verify the completed installation with you. And it's not just about lighting. They obviously come around and check everything where the points have come from before they issue the certificate. And with lighting, they are, they're not necessarily lighting experts, but they do have a prompt sheet and they know what they're looking for. So you would probably have to attend site with certainly an illumination level meter, a drawing and a calculator and a tripod, and they would want to see you taking measurements to prove the vertical illumination and the horizontal illumination, and then convert the vertical illumination to melanopic content so that they could tick that one off ready for the certification for the building. So there will be some commissioning or verification attendance required to work with the well assessor on lighting. I say this is interesting because some customers say to us, we want you to design the lighting to the well 2 standard, but we're not going for the certification. We just like the standard. We think it's very good. And it is quite a good standard as a lighting standard. So some people are having lighting designed to well 2, but they never intend to go for the certification for various reasons. And then we have people with older projects saying, can you assess our lighting design or our completed installation and tell us if it complies with the well standard, which basically is again, customers trying to get something for nothing. It very rarely works. We probably get 80% compliance. And then we have to say, if you want to get that extra 20% for full compliance, then this is what you've got to do to that installation. And obviously it comes at a bit of a cost. So quite often those are older projects that may have been initiated 3 or 4 years ago, a bit of a slow burner, and it's just coming up to the point, where it's about to go into construction, and along the way the customer's heard about well 2 and thinks, oh, this will be a good certificate to have on the wall. Let's see if we can get that one as well out of this project. And it's not always that straightforward. If you are going to do verification of lighting or commissioning, then you can actually develop a commissioning method statement from CIBSE Commissioning Code L. It's basically a series of pro formas and a management process, so you can actually use those pro formas to create a commissioning method statement for well 2 as well. There are 3 worked examples in the appendices of Commissioning Code L for a small, medium and complex project. So if you're familiar with that document or you have a look at it, particularly the worked examples, you'll see how you could produce a commissioning method statement for well 2 verification. Again, power calculations with any lighting now, particularly as we're, become very conscious on power consumption for all electrical services. Bearing in mind we have 2 different modes and we'll also have automatic lighting control, then the average power consumption is going to vary at different times of the day. So, if we put this on a timeline, from 9 o'clock in the morning to 1 o'clock, we're going to be in mode 2 and the building's going to be occupied. Is probably when the lighting installation draws its most power. And then in the afternoon, it goes, from mode 1, then in the afternoon, it goes back to mode 2, where it's just a standard photopic installation. The power should go down a little bit. And then when everybody goes home and it's still in mode 1, maybe the cleaners pop in and out. you're probably not going to have the lighting on. There'll just be a small standing load. So there's really at least 3 different levels of power that are going to be used during the day, and you should run it through a Lenny calculation to take into account the benefits of the lighting control and any daylight linking. So I've been experimenting recently with breaking this all down with a spreadsheet to get a more accurate lighting energy model. And once you start using Lenny as well, you tend to find that you get a better outcome than just sticking at watts per square meter. The number sometimes can be a bit frightening because, as I said, with power density in watts per square meter, it's always at 100% lighting output, and it doesn't take into account the effect of lighting controls. So in conclusion, I'll just get this up on the screen. The WELL standard is evolving, but it's not unique to best practice lighting in the UK and Europe. I would say that a lot of the things we're seeing in the WELL 2 standard, particularly regarding melanopic lux levels, this is, at the moment, it's really only the WELL 2 standard that are speaking about this and specifying it. But I think you'll find within the next few years, this whole idea of the melanopic content of a lighting installation will become commonplace on all decent specified projects. It won't stay the preserve of WELL for long. It is going to start to spill out soon. In fact, there's already moves afoot to develop a British standard on wellness, which I've seen a draft of, and this is included within that standard. In terms of good lighting design, BSE N12464 Part 1 is your go-to standard, whether it's a WELL 2 project or not anyway. And then there have been some tests done, actually. There was some CIBSE R&D funding put to the Building Research Establishment in Watford, and they tested 3 different methods of delivering and measuring melanopic content in electric light. So they tested the EML or the MDEI method, which are still valid, but you have to convert the metrics. They're not SI units. The SI units have only recently been released, which is the MEDI method. There's a slight change there, but you can still convert between melanopic equivalent daylight illuminance and equivalent melanopic lux. It's just a simple conversion factor, and I think by the next revision, once everybody gets their head around this, the WELL standard will probably drop EML and they'll just leave MEDI in there as an SI equivalent metric. There's another one called CS, circadian stimulus. This is more difficult to achieve, and it's not an SI unit, so we expect to see that fall by the wayside. So what the BRE concluded was, is of the 3 methods, the EML method, which is at the time was used in the WELL standard, is the easiest one to engineer with and develop a result on. The MDEI method appears in the German DIN 5031-100 standard, which don't really see specified in the UK, and in fact the DIN Institute have had to revise their standard this year as well, because the new melanopic equivalent daylight illuminance SI equivalent metric has come out, so they've had to update that standard as well. So this whole science of melanopic lighting, circadian stimulus, and the codification in the standards has been very much evolving in the last few years, and to be honest, the science is not yet finished, so we expect to see some more evolution coming in the next few years as well. But you know, WELL 2 has said, I'm drawing a line in the sand, this is where I'm going to start from. So that's it. So that's the end of the presentation. I will hand back to our presenter and we'll see if we've got any questions in the chat box. No, or otherwise, if people want to unmute, if they've got any questions, we can have a Q&A session now. Ella, are you there?
Oh.
I
was coming on to respond. All delegates, you can, if you wish to, now unmute yourselves. Apologies, my mother's ill in the background if you heard the coughing.
Okay.
Yeah, okay, so does anybody have any questions for Sophie? Well, just while people are thinking, I was wondering, Sophie, you've presented a conversion from the photonic Yeah, over to
Melanopic, yeah.
terms. Yes, but just one simple number. But at the beginning, you'd shown the different spectral outputs of different types of LED light sources, and I'm just wondering, does not the quality of the light source make a big difference?
Oh, absolutely. That division, that number I showed you, that multiplier towards the end, that's a mean average for the entire visible lighting spectrum of a luminaire. So that will be displayed on the data sheet. But you're right. I mean, if you really wanted to, you could break it down in much further based on that spectral analysis I showed you, but it wouldn't be practical really in terms of producing a design. I was actually looking at some research papers earlier today where they are talking about doing something along that line, where you have up to 11 different lighting channels within a single LED chip, all delivering slightly different forms of light and blending it together. That's something that the academics are still talking about. Somebody's written a paper about it. There may be something in it, to be honest. It's what we call, as a science, we call metarisms, and it would probably take 5 to 10 years before it could be commercialized, if it could be commercialized. So like a lot of these academic papers, they are desktop exercises with a certain amount of laboratory work, but actually making the leap from the laboratory into actually developing it and proving it and saying there is something here that's technically superior and can be commercialized, and we can also break it down in a way that day-to-day engineers can engineer with this and produce designs and have software tools, is the biggest part of the work. And what I saw today is just the start. It could be many years before it gets to the point where we could actually talk about it and show a worked model of how to work with it at, say, an engineer level, perhaps as we do day to day. But yeah, as I say, the science is not finished yet. We only know there's still sensors in the human eye that we don't even know what they do even to this day. The scientists are still trying to work that out. And certainly what I discussed here about providing a melanopic content for 4 hours of the day, people quite often say to me, could you do that for people working night shifts and give them a sort of a circadian boost through the night so they're more productive if, say, they were working in one of these Amazon warehouses or something like that? And the answer is no. Because the science hasn't been developed yet. We don't know if we would actually be introducing medium to long-term health problems by going against nature, where normally that person would be in bed asleep at 3 o'clock in the morning, I'd like to think, rather than working a night shift. But I know that's the reality. But actually boosting people's or suppressing people's melatonin at 3 o'clock in the morning, it's not been scientifically proved as a safe thing to do. And if you speak to the scientists behind this subject, it's something they've still got to get round to. And I do know that if people who do work night shifts, particularly nurses, if they do it for a number of years, they are more prone to breast cancer later on in life. So that is an established medical fact. So we have to be very careful with this, that we don't go into a territory that has no scientific basis. Otherwise, the client may be delighted with the result initially, but their insurers won't be so delighted further on down the line.
Yeah, no, absolutely, quite valid.
Yeah.
Yeah. The other thing I was wondering was you're talking about either increasing the lighting level or shifting the correlated color temperature for that period. When you switch from one to the other, how is that a gradual switch or is it like an instantaneous switch, and how do people respond? Yeah,
that's an interesting one. That we did quite a bit of work on the psychology of changing electric lighting in terms of human beings a few years ago. So where we started off is that if you dim lights very quickly, so say you've got an automatic lighting control and you drop the lighting level, say over 2 or 3 seconds, almost instantaneously, people are worried by that and they think there's something wrong, and they're most likely to phone the FM manager and say, you might want to come and take a look at this. The lighting suddenly, dropped. But if you take it very slowly over, say, 20 or 30 minutes, which you do with a daylight linking system, they get used to it psychologically, and it's no problem. They probably don't even notice it. But the true is opposite. If you take the lighting levels up, if you ramp the lighting levels up, say over 2 seconds, people take comfort in that, and they're not spooked by it at all. So good quality lighting control systems that use daylight linking. They have an algorithm in it. So when they're going to dim the electric lighting because there's more sunlight available, they will do it very slowly and gradually, so it's not a shock to people. But when they need to come back up, if suddenly the sun goes behind the clouds or something, or somebody closes the blinds, it will come up quite quickly, and people will take comfort in that. And it's the same with color temperature as well. If you're going to adjust color temperature, you need to do it perhaps over 10, 15, 20 minutes, because if you get these sudden massive changes, people will notice it. But to be honest, most people wouldn't notice a shift, say, over 2 minutes from 4,000 to 5,000 Kelvin. So, but if you did it straight away, if somebody said, well, look, the only way we can get the numbers to work here is to go from 4,000K to 6,000K, and you did it over, say, 2 minutes, people would notice, and they probably would pick up the phone to the maintenance department. So there's a lot of psychology between what you can do with lighting in a space and how people react. Yeah. And the BRE have done an awful lot of work on that.
Yeah, no, that's great, fascinating. Just one final question then: how do people notice a big difference coming into a space that's been designed to the WELL standard in terms of the lighting compared to another space?
Yeah, particularly when you introduce daylight, and as I said in the presentation, it's always a balancing act. How much daylight can we introduce for wellness and to make it a pleasant place for people, and then go across that line where suddenly we're introducing solar gain, and we're having to use a lot of air conditioning in the summer, and people are complaining on one side of the office that every time they look up in the morning that they're getting discomfort glare. I think if it's well engineered and thought out, particularly where you've got daylighting in and daylight simulation, people tend to find it's a much more enjoyable place to work. So it's very difficult to measure the anecdotal or the feedback from people. We did look at one project with the BRE where they developed a questionnaire, but what they discovered when they computated all of the data is sometimes people come to work and they're a bit grumpy because perhaps they struggle, they had a bad commute or something, so they're going to respond negatively anyway, if they didn't have a good night's sleep maybe. So people are very, very subjective. So there's actually a project at the moment to streamline these sorts of surveys for when these systems are being assessed, to make sure we're asking the right questions at the right time for the correct length of time as well, so that we can then just sort of average that data and iron out the people who gave us negative responses on the odd day, which are influencing the results because perhaps they struggled to get into work, or they didn't sleep too well the night before, or they just had an argument with the boss or something like that. So yeah.
Yeah, okay, well, thank you so much. Does anybody else have a question for Sophie? No, well, I think in that case then it's just, thank you ever so much for a very interesting presentation, and yeah, really valuable, and thank you for your time.
Okay, thank you very much. Okay then, good evening everybody. Bye.
Thanks, Sophie, it was excellent.
Bye.